Hello everybody, and welcome to exercise 1 on page 46 of the workbook. Let's take a look at this problem that they're asking us to do. So the temperature in a spherical portion of space is given by this formula in degrees Fahrenheit, and x, y, and z are being measured in meters. And they'd like us to determine how fast the temperature is changing if we move away from the point 112 in the direction of the origin. Okay, so you might recognize this as asking us to calculate a directional derivative. Let's start by making that observation. And just to maybe have a visual picture in our mind of what direction we're moving in, let's draw a picture. Okay, so they tell us that we're starting from the point 112. It's maybe sitting somewhere up here. And we want to move in the direction of the origin. Okay, so we're kind of going from here to here. I'm going to give that vector the name v. Okay, well, as we do with the directional derivative, we want to find a unit vector in the direction that we're moving. Okay, so how about if we start by writing down a vector for v? So if we start at the point 112 and move towards the origin, notice that v, that vector that we drew, is actually minus I, minus j, minus 2k, because we're going kind of backwards from 112 to the origin. Okay, and what we'd like is a unit vector that goes in that same direction. So u is going to be that vector v over its length. Okay, so we're going to get, let's see, negative I minus j minus 2k over square root of the sums of the squares of everything. That's going to give us a 1 plus a 1 plus a 4 if we square all of those. So altogether then, we're going to get 1 over the square root of 6 times our vector. Okay. And to find the directional derivative, we also, in addition to knowing the direction, we need the gradient for our function. So why don't we take a minute and calculate that? So the gradient of t, we're going to get by taking our formula and just taking the partial derivatives. So if we take the derivative of that function with respect to x, let's see, derivative of 2x squared is 4x. The y and the z come along for the ride. So we're going to get that for our first component. And then, let's see, derivative with respect to y. Derivative of y is 1, and the 2x squared z is going to hang around. And then finally for z, the derivative there would just be 2x squared y. Okay. All right, so we have the two pieces that we need to find a directional derivative. Let's go ahead and do it. So the directional derivative of t in the direction of u at the point 112 is going to be the gradient vector at the point 112 dotted with u. Okay, so to get the gradient of t at 112, we just need to jump back up to this formula and just substitute in 1, 1, and 2 for our x, y, and z. Okay, let's do that. So we'd have 4 times 1 times 1 times 2 in the first coordinate. That's going to give us an 8i. Okay, and then the second component, let's see, 2x squared, that's going to be a 2 times 1 squared times 2. That's going to give us a 4j. Okay, and then finally the third component, that's going to be 2 times 1 squared times 1. That's going to be a 2k. Okay, and we'll go ahead and dot that with the u that we wrote down above. Okay, and when we take that dot product, I don't know that we've used this little technique before, but that 1 over the square root of 6 that we factored out, we could actually take that and just move it to the beginning of all of this work, and then just take the dot product of the portions that are left over. That makes the algebra maybe a little bit easier. So we've got a 1 over the square root of 6 in front of everything, and then we'll take the dot product of these two vectors that I'm underlining. Okay, and if you do that, let's see, we're going to get a minus 8, minus a 4, minus another 4. Put all of that together, and we get negative 16 over root 6, which if we round it off to a decimal would be negative 6.53 roughly. Okay, there's our rate of change, and only thing left is what are the units? What are we measuring the rate of change of? Well, in this case it's temperature. Okay, so our unit should be degrees Fahrenheit, it looks like in this case, per unit distance, and that's measured in meters. Okay, and there's our answer.